Hi everybody, Kat Barger, Texas Christian University, and today we're going to be talking a little bit about the environment around galaxies. And so when we look around our Magellanic Cloud galaxies, we have lots of processes going on. We have beautiful tidal debris in every which direction. We have a tremendous amount of gas in the leading arm stream, the bridge region. If you add up all that gas in just the neutral phase, we're talking about something on the order of 800 million solar masses. Now, from some recent work by Andy and me as well, we're also finding that there's a tremendous more amount of material in ionized gas as well, pushing the numbers more closer to a few billion solar masses. And so we have a tremendous amount of gas around our two Magellanic clouds, but then just in general around galaxies, there's a lot of material. The circumgalactic medium around galaxies acts as a nice reservoir for future replenishment of gas and so forth. We have baryons swapping in and out of galaxies, and we really need to understand how those processes work and to understand how galaxies are growing. Now over here in our backyard, this is an excellent opportunity to study those processes in detail. Now, when gas is flowing between galaxies, in order for it to actually be accreted onto a galaxy, it is affected by numerous different processes. One such thing is that around our own Milky Way, we have a large hot ionizing halo, and that itself can cause the material to become ionized and evaporate as it's interacting with the coronal gas. In addition, we also have ionizing radiation that is expelling out of all galaxies. And so here is a model of what the ionizing radiation looks like escaping out of our own Milky Way, where we have the galactic radius here. We have the height right here above the plane. So, high Z, low Z over here, height 0 right here at the plane. And this region over here, it's really lit up. It's very, very bright because a lot of the ionizing photons are being produced there, as that's where a lot of the star formation is. And so you have a lot of ionizing radiation escaping along the poles. As you go through more and more of the ISM, it's harder for that ionizing radiation to escape. So now, with this model though, what about the Magellanic clouds? They're also contributing ionizing photons around as well. And so we're going to be talking about that today. So a little bit of context, why we even care. Well, when you think about how the universe has evolved itself, we really need to understand how ionizing photons are leaking out of galaxies. They've influenced the formation and growth of galaxies. They're still influencing them today, making it maybe difficult for them to acquire new material to keep forming stars. Now over here in the LMC and the SMC, it provides us a great opportunity to kind of figure out how ionizing radiation is escaping out of smaller galaxies. But we can also use that, look at that in a different way too, is that by understanding how it's escaping out of these galaxies, we can also kind of think about, did these galaxies maybe look like a progenitor for our own galaxy? And so we can use this for understanding our own galaxy at an early time. Now, another reason why this is difficult, just in general, is if you look at galaxies that are farther away at higher redshift, you have a hard time knowing what orientation, inclination angle they are, and oftentimes you only get one direction as far as how much UV flux there is. And then plus, if you want to know how much radiation is escaping, the escape fraction that's coming out of these galaxies, you need to know how much UV flux are producing as well as how much is escaping. So it's really hard to disentangle all of that. So our nearby galaxies really help us with that. So we're going to focus in on this bridge region, and here we have the Magellanic Bridge in H1, where we have the SMC tail region, and the bridge as well as the LMC over here. Now I went and I observed this whole entire region in H alpha using the Wisconsin H alpha mapper as a graduate dissertation project. And here is an example of some of the spectra that we saw, where we have that SMC tail region over here, the region between the two galaxies, the bridge region, and over here a region next to the large Magellanic cloud itself. Where the red over here in these spectra, that's tracing the ionized H alpha emission, the black is tracing the H1, and so you can see that there's a lot of complicated stuff going on here. We see some very, very bright H alpha emission. There's multiple component structures going on over here and so forth. But the beauty of this instrument is that we can actually just map out the entire structure. And so we mapped it out, and this is what we saw when we looked at the bridge in H alpha, where we see that same kind of general morphology that we saw before. We have the SMC tail, we have over here the bridge region, the LMC, figuring out how ionized it is, we have something on the order of maybe up to 50% ionized in the very central region, and then a little bit less over here towards closer to the SMC galaxy. Okay, so we see that there's a plethora of ionized gas out there, but what's actually causing this ionization? Well, there's numerous different sources, and we have to kind of think about all of them, but we're going to kind of do things easy, do first order kind of figuring out. It's always better to start easy than it is to start out complicated. But here's the complicated, where you have different sources of photoionization, different sources of collisional ionization. Now, for simplicity, we're just going to simply ignore the collisional ionization and see how well we do. In order to do that properly, you do need multi-line observations, which I actually do have, so I'd be happy to talk to you guys about that later on. Okay, so for photoionization, what sources do we have? Well, we have the nearby Milky Way, which is right next door. We have the extragalactic background, ionizing radiation from galaxies far, far away. Early type stars within the bridge itself, as well as the neighboring Magellanic cloud galaxies. Okay, so here's what we see when we look at how much H-alpha emission we have as a function of distance across the Magellanic bridge, where we have right here the location of the SMC center, the center region between the two galaxies. Over here we have the LMC, and so this is angular distance over here. This is a log scale of how bright the H-alpha is. Now, H-alpha, as it's a recombination line, it's directly related to whatever's ionizing it. And if we're playing the game that photoionization is causing the ionization, then the amount of H-alpha you have should be directly proportional to the amount of incident ionizing flux. And so with that, you can then put on this scale over here, well, how much ionizing radiation do you need? And over here, we have little markings indicating how much contribution the extragalactic background gives you, how much the extragalactic background plus the Milky Way gets you. And you can see that we're all the way up over here. So we're much higher. And so right here, order of magnitude too low in order to reproduce how much H-alpha we're seeing in the bridge region. Now, a couple things to point out. Of course, we get very, very bright right here, and we get very, very bright right here. But that's also not too surprising as we're right next to the Magellanic cloud galaxies, two sources of ionization. Okay, so how are we doing over here? Well, when we look, over here, we're a factor of 10 too low. Now, what Claire actually showed earlier is that there's regions in the bridge, if you look at the location of where the early type stars are and you look at the bright H-alpha emission, what you'll find is that they're not very well correlated. And so you can argue that maybe they're not the dominant source of that photoionization. Now again, feel free to talk to me about multi-line stuff another time or afterwards. So with this kind of really points out to us being able to say a lot of that ionization can actually be coming from the Magellanic cloud galaxies themselves. So we can use that to estimate the escape fraction of ionizing photons from them. So in order to do that, we have to do a little bit of modeling. We have to think about how exactly we're looking at the Magellanic clouds. So if we have us here over here peering at the Magellanic clouds, this one at 60 kiloparsecs away, this one at 50, here's what their disks look like. Cartoon representation. Now the SMC is actually an irregular galaxy, so, but these two galaxies right here, they can shine on each other and all kinds of stuff. So, they're emitting ionizing radiation. That ionizing radiation is hitting everything around them, as well as the two galaxies themselves. Okay, and we have to account for their projection angles, inclinations, and all those kind of fun things. Here's the H-alpha map that we did over here, and we radially summed up how much H-alpha emission we had in this region right over here. Now, here's the resultant model for what we found, where we have that same figure that I showed you before, but with a little bit more drawings on it, where we have the combined estimate for how much ionizing radiation is escaping from these two galaxies shown here in purple. This is the estimate for just the LMC galaxy itself. Here is it for the LMC galaxy itself. Now, a couple things that I want to point out is that notice that this kind of bowl right here is like asymmetrical. Now that asymmetrical U shape is actually just comes out from the fact that the SMC is farther away than the LMC. And so that just comes right out. Like we didn't have to do any tweaking for that. And then the height of this is basically scaled with how much H-alpha emission we have that we see. We know we have predictions for how much ionizing radiation these galaxies are producing because we have an idea of the star formation rates of those. And so the amount that's escaping, the amount that they produced, And so we can calculate their escape fractions over here. And so what we then get is we then get something on the order of around less than 6% for the LMC and around less than 4% over here for the SMC over here. Now I want to emphasize that these over here are definitely upper limits, and so these are average amounts for how much it is escaping from the entire galaxy. Remember, if you look at different locations around the galaxy, the flux could be higher or lower depending on which part of the galaxy you're looking at. But I want to emphasize that these are upper limits because there's many things that we haven't accounted for here, including things like the shape of the LMC is not a disk, it's irregular. But actually just doing that for that cartoon, it seems to work out pretty well. We're not including collisional ionization or anything like that, so that can actually lower the number as well. But you can see that this number actually is pretty low already as is. And it kind of tells you something about what's happening with that galaxy. When I think about all that feedback, all those beautiful pictures that people showed earlier with all those shells and so forth, the ISM in these galaxies, it's very, very patchy and there's holes everywhere. And to me, that just tells me that ionizing radiation should be leaking out like crazy. And so in my mind, it's like, well, why isn't there ionizing radiation leaking out? And so what I believe is happening is that, yes, there's a lot of holes, but with all that activity, we're actually proofing out the ISM as well at the same time. So just because it's more proofed out, that counterbalances the ability for the ionizing radiation to escape out of that. Okay. So I wanted to show you what this cartoon now looks like, where we have the same model over here where we had for the Milky Way, but we can now add the contribution over here from the SMC and LMC and actually see what that ionizing radiation looks like in a more of a 3D thing. Now this is of course a 1D or a 2D slice of that model and so forth, but now we have predictions for what their contribution is too. And so we can also use that to figure out what's happening with the stream. How much time do I got?
Not much. We have 2 minutes for questions.
Oh, okay. So the only other things that I guess I'm going to point out is that in order to improve this, yes, multi-line stuff is definitely key. We also have wonderful observations going on with the Magellanic stream, both in absorption and emission as well. Brianna Smart's doing some awesome work looking at mapping out the entire structure of the Magellanic stream and H-alpha emission. And we can put all of that together to test to make sure that these escape fractions are robust or even to refine them even further. So that's what we're working on. Thank you.
Anybody has questions? We have a few minutes. Yes, Andy?
Yeah, about the low escape fractions. I totally agree. It's puzzling because you mentioned all the holes in the H1 distribution. Mm-hmm. Also, the SMC shows a lot of signs of tidal disruption, right? It's clearly been interacting with the LMC. It's thrown out all the gas that you see everywhere. So, do you have any comment on that? Even though the SMC has been distorted in many ways because of its interaction, it's still not letting out many photons.
Yeah, I honestly think that it has to do with the galaxies just getting poofed out with their ISM just being more poofy. That yes, there's holes, but if you spread out the ISM, it's going to block the radiation too. But that's not to say that this is puzzling. So there definitely needs to be more work for us to think about this. Yeah.
You threw up the bridge stars as being sources of ionization.
Yeah.
Because there wasn't spatial correlation.
Yes.
But if you somehow subtracted off the LMC and SMC fraction, could you then give a limit on just what the escape fraction from the bridge itself was?
So the next phase of this project, the last chapter of my dissertation, which part of it is done, but not the weed part, the surface part, is that I actually have multi-line observations of this entire region and sulfur 2 and nitrogen 2. Oh, shucks, I can't jump quickly. Here, we'll jump quickly like this. And the next stage is to really figure out what's happening with the sulfur 2 and nitrogen 2 to see how well that correlates with the star formation in the bridge region. And it turns out that when I look at the sulfur 2 and nitrogen 2, it looks like there's actually a low velocity and a high velocity filament. That's very similar to what Eric Muller found with the SMC tail region. And when I look at that, the high velocity component, there's actually a ridge line that has line ratios that are different from the surrounding of it. So I actually do think that the stars are influencing the gas, but from the H-alpha by itself, you can't actually disentangle that. But with multi-line stuff, that's really what needs to happen to figure that out. So I have the multi-line stuff there. Now, of course, there's the next complicated part of actually modeling it to figure out what that means. And that's the part that we haven't done. We've done the observations showing correlations and so forth, but we're lacking the modeling part because that's complicated. There's lots of ionizing processes happening at the same time, and knowing if it's turbulent shocks and how much photoionization. I mean, if you guys have ideas where to start, I'm interested.
All right, we have to move on, so thank you, Kat. And our next speaker